Alright, welcome to module 3.7. We're going to look at combustion reactions in this video today. So we're wanting to know what are the key characteristics of a combustion reaction, i.e. what makes a combustion reaction a combustion reaction. What are some examples, what are fossil fuels and what are their role, and we're also going to look at how to draw and name some basic hydrocarbons. So let's get into it. Alright. For something to be a combustion reaction, it has to meet two key criteria. If it doesn't meet both of these, it's not a combustion reaction. The first thing is that oxygen has to be one of the reactants. So on the reactant side, you have to see oxygen as one of the things there. The second thing is heat has to be released. Now, in an equation, you may not always see this. Sometimes it'll be a case of whether or not you're aware of the reaction, you know something's burning or something like that, and you know heat is being released. Other times, if it's in a test or something like that, and we know it might not be very clear, we will indicate if energy as heat's being released. Alright, so don't stress too much about that, but those are the two key criteria that a combustion reaction has to meet for it to be a combustion reaction. So if it has oxygen as a reactant but doesn't release heat, not a combustion reaction. If it releases heat but doesn't have oxygen as a reactant, not a combustion reaction. So it has to meet both of them. Alright. Generally, we use fossil fuels a lot in combustion reactions as the fuel source. They'll be the thing that's combined with oxygen. And fossil fuels is a very broad term meaning quite a number of things. And we'll look at what they can mean, later on. But generally speaking, fossil fuels are made up of two key elements. They're made up of hydrogen and of carbon, and we very imaginatively call them hydrocarbons. So a hydrocarbon is just a molecule that is made up of hydrogen and carbon. It's not the most complex of words there. The word combustion actually comes from Latin, again. This time it comes from Latin word combure, which means to burn. So we tend to associate combustion reactions with burning because that is where that word has originally come from and what it was initially associated with. Alright, so now that you know a little bit about combustion reactions, can you think of three other combustion reactions that use fossil fuels? Pause the video, have a bit of a think, and we'll go through some on the next slide. Alrighty, so some examples might be electricity generation, where we burn coal or natural gas or biomass to generate electricity. We do combustion reactions in cars or in other forms of motor transport where different forms of crude oil might be burnt. Jet aircraft burn kerosene to fly. Fireworks is a form of combustion reaction. Rocket launchers use hydrogen and react that with oxygen to react and produce water. So those sorts of reactions are lovely and clean because the only byproduct you're actually producing is water. But they're a bit tricky to control. So unfortunately, we don't as yet drive cars that are powered just by hydrogen and only produce water, which would be lovely and would definitely help the environment. But those are some examples of combustion reactions that we see. And we've got a bit of a video here, thanks to Mythbusters, on a bit of some fun stuff you can do with combustion reactions. So we'll have a watch of that.
So Adam and Jamie have got explosion envy, and to soothe their egos, they're going to weave some homemade magic of their own. First out of the blocks is Adam, and he's intending to set the World Wide Web alight with a towering inferno of soapy water.
We're trying something an old friend of mine gave me, which is that if you bubble methane up through soapy water, you'll end up with a column of bubbles. Because the methane's lighter than air, it helps lift the column and keep it stable. And then when that column gets a certain height, however high you want it, you can light it and the whole thing goes whoom in flame.
And with a garden sprinkler on the end of a methane hose in a bucket of foamy water, it's not long before he has his very own bust of bubble.
I have been a bubble sculptor for about 20 years. The bubbles are a very fine way to sculpt the real world.
Their first attempt is a little lopsided, but Adam is poised to feed the fire of his pyromania.
That is so cool. It's water and it's burning. And now it's gone.
Second time around, and for Jamie and Adam, it's onwards and upwards. The bubbles are sticking together nicely, and the lighter-than-air methane is pulling the flammable column skywards.
At first, it's like, okay, it looks like it's working, but then it starts to get out into the area that defies physics.
Not only is it getting more fascinating, but it's increasing in funniness every minute. Okay, you ready? I just don't want to lose it. Wow! That was like a movie. That was like the beast dying at the end of the movie.
Well, I don't see anything on fire up there.
That was really cool. I have to say, for my money, that rivals the Canyon Soda. However, the Canyon Soda, that's safe enough for any 4-year-old to do. I mean, at least they're safe from everything except getting yelled at by their parents. This one, it's not safe pretty much for any of our viewers. We've done it. No, you don't have to.
Alrighty. Now, combustion reactions don't always have to just happen in the world around us. They can actually be happening inside of us. There is one particular reaction that we know about that really is actually a combustion reaction, and that is the process of what we call cellular respiration. We do this, other organisms do it. It actually happens to be a combustion reaction. In detail, the reaction is glucose plus oxygen, produces carbon dioxide, water, and produces energy. In fact, it often produces heat energy. Were you to do this outside the body, you would definitely find, obviously, oxygen is one of the reactants, and you are getting energy released. Inside of us, some of that is released as heat energy, and some of it is converted into other forms of energy to be used later. But if you were to do this reaction outside of us, say you were to take some glucose and you were to burn it, you would find it releases a lot of energy. Very thankfully for us, our bodies actually break this down to even smaller steps in such a way that they don't have that massive release of energy, and so we don't catch on fire every time our bodies try and do this reaction. So we are doing this form of combustion reaction in us all the time, but it is one that our bodies do in such a way in the mitochondria that it's nicely broken down to all these neat little steps, and we don't spontaneously combust every second or anything like that, which is really good because I like not being dead. So that is one example of combustion that you are currently doing. All right, let's talk about fossil fuels. Fossil fuels are formed from decayed plant and animal matter, generally thought to occur over hundreds of millions of years. So basically it takes a really long time for this stuff to sort of break down and turn to fossil fuels. The first example is coal. Now, coal is made mostly of carbon, and we mainly use this in generating electricity, particularly where we have coal-fired power plants. The next type of fossil fuel is natural gas, and this is methane. So methane is a carbon with 4 hydrogens around it. And we use methane in gas stoves and in jet engines, and we use it in a whole range of other places, but those are just a couple of examples. Finally, crude oil. Crude oil, that's what we're dredging up from inside the earth. It's mainly made of hydrocarbons, but it's actually quite a big mix of hydrocarbons of varying lengths. Some are much shorter chain hydrocarbons, some of them are really long ones. And so it's really a mix of chemicals, and we break it apart and we'll get diesel from that, we'll get normal petrol, you might even have tar in there, depending on how big those chains are. So this is what I'm talking about. You can see here we have a very small molecule, methane, but as we go down the list, we end up with decane, and you can get bigger than this, and it's quite large and quite long. And what's really interesting is when they're very small, they have very low boiling points. So methane is almost negative 200 degrees, which means at room temperature, it's going to be a gas because it would have already boiled. As we move up and the chains get longer, the boiling points get higher and higher and get closer to 0, and then they pass 0. And you can see there with pentane, its boiling temperature is actually about our normal body temperature. So once you get sort of past pentane, you would expect these things to be liquid at room temperature because they haven't actually yet hit their boiling point. But if you heat them up enough, they will boil and they'll turn into a gas. And this is actually really handy for the way we separate them. So these are all generally mixed together in crude oil, and we want to get them separated. So what we can do is we can take a sample and we can have it at a set temperature. And if that temperature is below the boiling point of that hydrocarbon, then that hydrocarbon will stay as a liquid. But anything that has a boiling point below that temperature is going to evaporate and turn it into a gas, and we can then distill that off and collect it. The process is called fractional distillation. It's called distillation because that's the name of the process that they're using, and fractional because we break the crude oil into all its little components, all its little fractions. So that's where the word comes from. So yeah, different hydrocarbons are separated according to their different boiling points. Now, what about the future? Because the world's reserves of fossil fuel are limited and they will eventually run out. So we are looking at alternatives to fossil fuel. This could be your solar energy and that sort of thing, but we have a few other ones that are sort of almost alternative sources of fossil fuels in a sense. So we have biogas. Now, biogas is where we have biomass, which is just plant and animal tissue, and as that's rotting and breaking down, it produces gas when it's in the presence of oxygen. So it can produce this whole mixture of gases, and it's just made from this decomposing matter. It's the sort of thing that might get made over a rubbish tip and that sort of thing. The stuff is rotting and whatnot. So that's one thing we can do. We could collect that gas, then we could use that in maybe instead of methane that we've mined or something like that. The other thing is ethanol. Ethanol is it's an alcohol that is produced when we ferment sugar. So this is actually what we produce when we're making something like beer or wine or spirits. It's actually ethanol that we're making through fermentation. But we can actually use ethanol because it burns really well, and we can use it in combination with petrol to help fuel motor vehicles. This isn't something off in the future. This is something we're doing right now. So we actually do sell a blend of ethanol and petrol available in Australia. It's called E10. You can see over here a little icon, and that's sort of what you might see at the petrol station, where you can get the ethanol and petrol mix. So yeah, that's one thing that we can do. Not all cars, unfortunately, can actually use this. So it's sort of a future thing, but we'd need to have a bit of a change for some car engines before we can actually use it across the board. And it is a case of it's about 90% petrol and only 10% ethanol. So it's not a great proportion of ethanol yet. All right, we've got some questions there. So I want you to pause the video and see if you can answer them. If you need to look things up online, go for it. But pause the video and when we come back, I'll go through some answers. Alrighty, so question number 1, what is the difference between ethanol and biogas? Alright, well, like I was saying before, biogas is a mix of gases and that's made from decomposing matter. So it's quite a range of different compounds and it's made in quite a different method. Ethanol, on the other hand, is a type of alcohol that is made through the fermentation of sugar. So it's quite a specific thing. It's one specific molecule. So those are the differences between the two, and we obviously can use them in different situations. Question 2, what is the difference between renewable and non-renewable energy sources? All right, well, non-renewable, generally we're talking about something that is a finite resource. When it's used up, it's used up. Renewable resources are ones that it's a case of they're constantly being produced in such a way. So we might talk about solar power being renewable because the sun's not really going anywhere. It's going to keep producing it. Us using it isn't removing the source or degrading the source in any way. So question 3, why are renewable energy sources needed? Well, they're needed because those non-renewable ones are going to run out and they're starting to run out and they're getting more expensive, those non-renewable ones. So if we can actually have renewable energy sources that are actually good renewable energy sources and cost-effective energy sources, then they're a really good alternative to non-renewable ones. And they also are less likely to cause damage on the environment, generally speaking. All right, time to dig into a little bit of organic chemistry. So first things first, you need to understand what an organic compound is. So an organic compound is a carbon-based compound that will also contain hydrogen, aka hydrocarbons. So you'll find that these can also contain nitrogen, oxygen, other non-metallic elements, but they don't have to. They do have to have carbon with hydrogen in them. That is really important. Now, there are 3 main types of hydrocarbons we're going to look into. They are very, very similarly named. In fact, they're all one letter different. Alkanes, alkenes, and alkynes. So you can see there is that letter down the middle that changes. So let's have a look at the differences between them. If you have an alkane, every single bond between the carbons is a single bond. Okay, they're only sharing 1 pair of electrons. There's only 1 bond there. On the other hand, for alkenes, you are going to have a double bond somewhere in there. Now that double bond is not, let me say that again, it is not between carbon and hydrogen. It is between a carbon and another carbon. All right. Finally, alkynes, similar to alkenes, they have a special bond in there, but it's not a double bond, it is a triple bond. And same deal, they will just have one of them, at least the ones we're looking at anyway. You can get more complex ones that have multiple ones, but for us, we're just talking about the ones that either have one double bond or all single bonds. All right. If you want to work out what the formula is of an alkane, then it is a case of however many carbons you have, that isn't the number there is N. And for the hydrogens, you multiply that by 2 and then you add 2 onto that. So for instance, if you have carbon is 8, hydrogen will be 2 times 8, which is 16, plus 2, which is 18. So you would get that. We also, when we name them, the name finishes in ANE. So that tells us it's an alkane. So you can see down here, ethane has only a single bond here. Okay, and we can even count this up. We've got 2 carbons, so it'd be C2. If our formula is right, we go 2 times 2 is 4, plus 2 is 6. We'll count that up. 1, 2, 3, 4, 5, 6. There we go. So it's H6. And we can see it ends in ANE, so that tells us it's ethane. All right, over here with the alkene, its formula is a little bit different. It is CnH2n. So what that means is if, again, you had C was 8, H would only be 2 times that. So 2 times 8 is 16. All right, and unlike alkanes, their names end in ENE or ene. Often they're also used to make plastics, because they're really good at forming long chain polymers. So you can see down here with ethene, it ends in ENE, it has that double bond there, and we can even double check our formula. So we've got 2 carbons, so that would be C2, and if the formula is true, we should have 2 times 2, which is 4 hydrogens, and we've got 1, 2, 3, 4 hydrogens, so it's H4. All right, finally our alkynes, so they have that triple bond. Their formula is CnH2n minus 2. So we'll go back here. If C is 8, then H would be 2 times 8, which is 16, minus 2. 16 minus 2 is 14. Their name ends in yne or ine. Now the triple bond is actually very unstable, so they're likely to react because of it. And down here we have our example of ethyne. So you can see yne, that's how it ends. You've got your triple bond here, and we can double check our formula. We've got 2 carbons, so it'll be C2, and then H will be 2 times that, so 2 times 2 is 4, minus 2 is 2, and that's how many you have, 1, 2 hydrogens. So that is sort of a bit of a summary of alkanes, alkenes, and alkynes. A bit more info when it comes to them, and particularly how you name them. So there are 2 parts to their names. It's made up of the first part and the second part. So we'll call that the prefix is the first part, and the suffix is the second part. So the prefix will tell us how many carbons there are in the longest chain. So the first bit of the word is basically it's communicating a number to you, how many carbons there are. Then the last part will either be ane if it only has single bonds, ene if it has a double bond, or yne if it has a triple bond. All right, so down here we've got 1, 2, 3, 4 carbons. All right, so 4, if we look on our list here, 4 is bute. It says but it's pronounced bute. So we have bute, and then it's only single bonds, so we use ane, so ane. So it is butane, and that is how we work it out. So you can see over on the side here, we have a list telling you if there's this many carbons, this is the prefix you put at the start. Now, the first 4 are a bit odd. They're not like what we're probably used to from maths and that sort of thing. So 1 is meth, 2 is eth, 3 is prop, 4 is bute, then goes 5 pent, 6 hex, 7 hept, 8 oct, 9 non, 10 dec. If you were doing 11, it would be undec, 12 would be dodec. So from 5 onwards, it makes sense with what we'd use for like a shape and that sort of thing, but 1 to 4 is a bit odd. So we tend to say 1 to 4 is meth, eth, prop, bute. All right, so that is how you name them. So you've got a prefix and a suffix there. All right. Here are 4 examples. I want you to see if you can have a go. Pause the video and see if you can work out what they are. All right, pause it and have a go. Alrighty, so let's go through these. All right, this first one up here has 1, 2, and 3 carbons. If you go back and look at the list, 3 is meth, eth, prop. So we know that this first one must begin with prop. and we can see it's got a triple bond here, so that tells us it's YNE. So our first one is propyne, sorry. All right, our second one over here has 1, 2, 3, 4, 5 carbons. So 5 we know means pent, P-E-N-T, and we've only got single bonds, so that must be A-N-E. So the second one is pentane there. Alrighty, down here we have 1, 2, 3, 4, 5, 6. 6 starts us off with hex, and we have a double bond in there, so it is E-N-E. So we've got hexene there. Alright, lucky last. We've got 1, 2, 3, 4, 5, again like the one above it, so again it's going to be pent. But we have a double bond in here, so it's not pentane, rather it is pentene. Not Pantene, that's a shampoo and conditioner, but pentene. Alrighty, so that is how you can identify what a hydrocarbon is, or what its name is. However, sometimes you might need to draw one, so you might get a case of, here is pentyne. How do you draw that? Alright, so here we've got propene. So what you need to do is you need to look at the word and you need to split it in those two parts. What does the first part tell me about how many carbons there are? And what does the second part tell me about the bonds between those carbons? So here, propene, the prop means 3, and the E-N-E means double bond. Okay, so start by drawing in the number of carbons you need. So prop told us that you need to have 3 carbons, so we've drawn 3 in there. Then the E-N-E tells us that there's a double bond, so we've popped a double bond in there. Now, with the detail we're doing on this, it doesn't matter where you put that double or triple bond, okay, as long as you're careful about making sure carbon doesn't have more bonds than it can make. All right, so we've got our double bond in there. Now, carbon cannot have more than 4 lines around it. 4 is its absolute max. And remember, carbon has 4 valence electrons. It wants 8, so it can put 8 more in there, which means it can only, it can't put 8 more. It can put 4 more in there to get 8. So it cannot have more than 4 lines or 4 bonds around it. All right, you need to be very, very careful with the alkynes, because sometimes that can mean you have a carbon with no hydrogens, and that's perfectly acceptable. So here we've got our carbon, and they've counted, so you've got 2 here between the 2 carbons, so 1, 2, and then you can add 3, 4 for the first carbon. For the second carbon, you've got 1, 2 over here, 3 over here, so you can only add 1 here for it. And for our last one, it's only got this 1 here, and then we can go 2, 3, 4. And then all you need to do at the very end is, if you've got an empty dash, just fill it in with a hydrogen on the other side. So that's all they've done at the very end. All right, you've got 4 examples here. Give that a whirl and see if you can draw what each of these look like. Pause the video now and give that a go. Alrighty, so let's go through these. So we'll start with propane. Okay, so that first bit tells us that there are 3 carbons. So we're going to go 1, 2, 3, and it ends in A-N-E, so they're all single bonds between them. Then I'm going to draw in my other dashes. So this carbon had 1, I can go 2, 3, 4. This one I've got 1 and 2, so I can go 3 and 4. And this last one has 1, 2, 3, 4. And then just go through and turn those all into hydrogens. Make sure you don't miss any. There's nothing worse than seeing somebody trying to draw their diagram and they're missing bits and pieces all over here and there. Okay, so that's propane. Draw that. Propene, the next one, P-R-O-P-E-N-E. Okay, same deal. It also begins with prop, so we have 3 carbons. 1, 2, 3. But it ends in E-N-E, so we know we have to put a double bond somewhere. Let's put it here. Oh, that's a triple bond. Oh dear. Okay, there we go. So we've got our double bond there. All right, so now we're going to go through and we're going to draw in, we're going to draw in our other single bond there, and we're going to draw in our hydrogen line. So our first carbon has 1, 2 bonds already, so it can make 3 and 4. This carbon in the middle is already making 3 bonds, so it can only have 1 more. It doesn't matter if you put it on the top or bottom, it's sort of just whatever you want. So that middle carbon has 1, 2, 3, 4 bonds. And the one on the end here has 1 and make 2, 3, 4. All right, then we go through and fill in our hydrogens. And there you go, that's propene. All right, let's do propyne. Okay, again, we're going to have 3 carbons. 1, 2, 3. This time we have a triple bond. I'm going to put the triple bond here because I feel like it. And we've got a single bond between those 2. Then we're going to go through and do our hydrogen lines. So this first carbon has 1 already, so you can go 2, 3, 4. The one in the middle, count them up, it has 1, 2, 3, 4. So that one in the middle can't make any bonds with hydrogen because it's already saturated with 4 bonds. And the one on the end has 3, so it can have 4. It can have 1 more bond. So hydrogen, 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 hydrogen. There you go. All right, hexyne. So all right. Hopefully we can fit it in this space. So hexyne has 6 carbons. We're going to go 1, 2, 3, 4, 5, 6. Okay, and we're going to put in a triple bond here. 1, 2, 3. And so our first, we have our other bonds, sorry, all of the other bonds are single bonds, by the way. And our first one it's already got 3 bonds, so we'll make 1. This one here, number 2, already has 4 bonds, so it can't do any more. This one, number 3, has 2, 3, 4, 1, 2, 3, 4 for that one. And for this one, 1, 2, 3, 4, and for our own one, it has 1, 2, 3, 4. We'll go in and fill in our hydrogens. Alrighty. Now with the hexyne, you could have put that triple bond the second after the second one, after the third one, after the fourth, after the fifth, or whatever. It doesn't matter. Alrighty. So that would be how you would draw hexyne. Like I said, you could put the triple bond elsewhere, but you would end up with the same number of carbons and hydrogens. You just shuffle around where they are exactly. Alright. So if you need a bit more practice with that, you can always make up a name and see if you can draw it, or you can draw one and see if you can name it and go that way about it. All right, so that is combustion reactions and hydrocarbons. So if you didn't get anything or need to go back over anything, you can rewatch this video, speed it up, slow it down, go back and watch those bits you need to see. And remember, you can always ask your teacher if you've got any questions on this content. All right, thanks for watching, and that is all.